Okay guys, so today we're going to be doing this lab where we're going to be investigating Newton's second law. Okay, we want to make sure that that whole F equals m times a vector sum of all forces thing we've been using for 2 weeks is valid. Okay, so the way that we're going to test that is that we are going to use a system, kind of like what I'm building up front here, that's going to involve a level track, okay, with a pulley on the ends. All right, we're going to connect the string to the cart. This is the front end. That's important. Otherwise you're going to get that the acceleration is negative when it pulls it down the track. No one's ever done that by accident in this class. Not one time. No, you haven't. So you have to just say, yes, I never did that. Okay, so you're going to tie that string. It's got a little anchor. Okay, the cart has a little anchor on the front here. That's where you should tie it. Please don't tie it to this black thing. There's actually sensors in this thing, okay, that measure like force and stuff like that. So we don't want to attach a string to that. Okay, attach it to the anchor here at the top. That'll also conveniently make sure that your vectored force on the pulley is level. Okay, they're pretty much the same height, right? Because we don't want that force to be upwards at an angle. We want it to be pretty much straightforward on the cart. And putting it there also allows for that to happen. Okay, so we want to set it up like that. Okay, so you're going to have a setup that works like this, and you're going to need to double knot that because this string really slips. Okay, like so. You'll have the cart on there, okay, and make sure that it's actually in the grooves, whether you have a wooden ramp or a metal ramp. On the wooden ramps, just be aware that the pulley has to be hooked to the little piece of meter stick that's taped to the end, okay? Because the boards are actually too wide for the gap in the pulleys, okay? So you'll actually have to attach the pulley to the ruler, to the little piece of meter stick, and it'll work just fine from there. Okay, all right, let's talk about the design stuff here. Okay, so what we're testing in this lab is what relationship exists between the applied force or the force applied to an object and its acceleration. Okay, and we are going to be looking at some variables in this lab. Now, in this lab, we are comparing applied force to the acceleration that it produces. Okay, so to help you with your design part here, here's what's going to happen. You're going to have your cart on the track, and you're going to hang some masses over the pulley. But you're also going to have some masses on the cart. Okay, so your first trial, and I'm just making up numbers here because I don't remember what they are off the top of my head. Okay, so in your first trial, you're going to have a little bit of mass hanging over the pulley, which does mean, guys, that you have to tie a bit of a loop, okay, in this string at the bottom. Which is not hard, you just have to make sure you have a loop to hang the masses from. Okay, so make a little loop, and you're going to hang one of the masses off of that loop. Okay, and it's going to hang over the edge, and the other masses are going to be on the cart. Throughout the lab, we are going to move mass from the cart to the pulley. Okay? The more mass I put over the pulley, the more what I'm going to have. I will, but that's going to respond to what I'm doing. Okay? What I'm doing is I am putting more mass, or maybe we'll say more weight, over the end of the pulley. Okay? I'm taking mass from this cart and I'm putting it over here. And if I put more of it over here, it increases my what? Not acceleration. We've already established that that's going to increase. What am I directly changing by putting more weight over here? Force. Okay? The applied force in this case is coming from gravity. Okay? And each trial, I'm going to move mass from the cart to the pulley to change that applied force. Right? I'm going to measure the acceleration of the cart in response to that change. Okay? Now, in terms of some other variables here. I'm having all of this mass in the system. All I'm doing is changing where it is in the system. But I'm never changing the what of the system. The mass of the system. Is that important? Why? Think about that when you're explaining why the mass of the system is a controlled variable, spoiler alert. Okay? There's a reason why we have to make sure that the mass of the system does not change. We've talked about that, I think, enough times for you to figure that one out. Okay? You also need, in addition to that, two other controlled variables. Okay? Think about the setup of this system, okay, and anything else that might affect the acceleration of the system were it not controlled. Okay? One very obvious force might be available to you as a controlled variable there. Okay? Everyone all right with that? Okay. This happens very quickly, okay, this experiment. But before I get to the procedure, let's talk a bit about the rest of it here. So that's the design part. That's as much as I'm going to give you for the design. Okay? For the hypothesis, okay, if and then statement that is a tentative answer to the problem. So in the if part, you should probably talk about Newton's second law. Okay? The if part of your hypothesis, okay, should be about what Newton's second law says about the relationship between force, okay, and acceleration. Right? That's going to be the if part, because that's what we're testing. Okay. The and part, describe the experiment. Okay? Various applied forces will be, or various forces will be applied to a mass cart system, okay? And the acceleration will be measured according to these varied forces, okay? The then part, predict, okay? What's going to happen to the acceleration of that system as you increase or change your applied force and why. Okay, so predict results. And a short why. Okay. Question so far? Okay. Remember that in your variables you're identifying and explaining. Okay. One manipulated, one responding in this lab, 3 controlled. Each controlled gets explained on its own. Okay. All right, so we're going to have all of these materials here, okay? And as we said, you're going to change the applied force by putting more mass over the pulley. Now, one of the other materials is going to be fun tack. Okay? The reason we need fun tack is because we are going to have masses on this cart. And if I just let the cart accelerate, what will the masses do? They'll try and stay put according to Newton's first law. Okay? And then the cart will slide out from under them like the tablecloth out from underneath the dishes. So you will need to put a little bit of fun tack on the bottom of any mass that's going on top of the cart. Stick it on there so it doesn't slide around. Okay? It doesn't need much, just a little bit to keep it from moving. Okay? All right. When we start this out, you're going to have a fair amount of mass on the cart and very little over the pulley. Okay? So the acceleration will be fairly mild. But as we move mass from the cart to the pulley, that acceleration is going to go up a lot, and you need to be ready for it. In fact, one member of your group has to be the person who stops the system before the cart hits the pulley. Okay? Because you have to do this one on a desk. You can't do this one on the floor. There's no room for the masses to fall. Okay, so this one has to be done on the desktop, okay, so that the masses have room to fall. Right? That means then if you don't stop this cart, it will Dukes of Hazzard over the pulley. Okay, probably break both the pulley and the cart. Right, and that would be bad. Okay, because these pulleys are actually pretty good. They're pretty low friction. Okay? They spin for a very, very long time, okay, for something, you know, made of plastic. Right? So make sure you treat the equipment well and be very careful so that the carts don't go flying. Okay? Because that last one especially is going to be fast, okay? And you're going to need to be ready. When you're doing the sampling rate, okay, it's one of the things you can change in SparkView. Okay, it's in the bottom left corner of the screen when you're changing it. You need to make that 20 hertz. Okay, it's usually defaulted to 20, but just double check it. Okay, you need this thing to be recording 20 times per second because you're not going to get a lot of data. Okay, those masses are falling and they're falling fast. Okay, so you need to have it recording 20 points per second. Okay, everyone with me so far? Yeah? So procedure, okay, we'll talk about the procedure, then I'll have you do it, then we'll talk about the rest of it. Okay, so you have this chart, okay, in your Google Doc, okay, or something very similar to it. All right, in trial 1, you're going to have the mass of the cart. Incidentally, the masses of the carts are written on them here on the blue tape. For some reason, the red carts are heavier than the blue carts. Don't ask me why. I guess red plastic is more dense than blue plastic, but every single one of them, the red ones are all 674, the blue ones are all 670. Okay, but we need it in kilograms, so it's 0.674 and 0.670 for the mass of the cart plus the masses. Okay, so for trial 1, mass of the cart in masses, okay, is going to be, well, it's actually not this number. The blue cart, sorry, is 0.274. Okay, you're going to have only 50 grams hanging over the pulley. Okay, and then you're going to calculate your applied force. You calculate applied force by taking the mass that's going to fall and multiplying it by what? What force are we using as an applied force here? Gravity. Okay, so if I want to calculate my applied force, it's the force of gravity acting on the hanging mass. Right? So times 9.81. Right? Your acceleration, you're going to get that by building a velocity versus time graph, okay, with your data. So when you've got all of your data, you're going to build a velocity time graph for each trial, and the slope of the line will be the acceleration. That's how you get the acceleration for each trial, because it's not something we're going to directly measure. Right? Everyone follow me on that? Okay. So your trials will go as follows. On the first one, okay, you're going to have 400 grams on the cart and 50 grams over the pulley. And then on each trial, you're going to pull 50 off the cart and transfer it to the pulley. Now, you're going to have to do a little bit of permutations and combinations here, because there aren't enough 50-gram masses for you to just easily pull them off and move them over. You might have to pull a 100 off of one and pull a 50 to the other, okay, in order to make it work. All right, but the masses are listed there, okay? 100 grams or 0.1 kilograms over the pulley, okay, and you're taking 50 off, okay, another 50 off of the cart to the pulley, another 50 off the cart and to the pulley. Okay, everyone with me on that? Okay, I'm not going to say anything else. I want you guys to get your data, and then we'll talk about what to do with the data after we have it. Okay, so everybody needs a track, a pulley, a cart, a box of masses, a piece of string that is a little tiny bit longer than the distance between the top of the desk and the floor. Okay, and some sticky tack, just a little bit to keep the masses on the cart. Okay. All right, let's get to it. Someone can use this one up here. Just don't take it apart when you're done. I need it for 34. Okay, so you want to whittle down your data till it looks like this. Okay, so you've got the time for run 1, probably about a second, maybe less. Okay, your velocity for run 1, velocity for run 2, velocity for run 3, velocity for run 4. I actually upped the rate at which I sampled run 4. That's why you see that it looks different than the others. Okay, I got more data points for that one because it just went fast, and I upped the data rate. Okay, but it's fine. That's what you need to whittle it down to. Once you got it down to there, we can talk about what you have to do with it. So now that everybody's kind of looking at their data, you got to do the same thing we've done with all of the other experiments. You're going to have to put it in Google Sheets and trim it down. Okay, that means like get it down to where you've got the 4 velocity data sets, okay, and the time for run 1. graph it, and then trim off the stuff that doesn't apply, you know, where you were holding it but hadn't dropped the masses yet, or after the masses hit the floor. Now, that's a key one. How are you going to know if you've got data that happens after the masses hit the floor? Right. The velocity should level off. Because once the masses hit the floor, what are they no longer doing? They're no longer pulling on the cart, and they're no longer accelerating, so the cart is no longer accelerating either. So be on the watch for that. You can see it pretty clearly on your graph when the acceleration begins and when it ends. We only want the during the acceleration part. Okay, so trim off all the fat, okay, so that we don't have those other things. In the end, you should end up with a graph that looks something like this one, right? You just have your velocity data with the accelerations. Okay, so run 1, run 2, run 3, and run 4. Okay, and I do see a fairly linear increase there. Run 2 and 3 are maybe a little closer together than I would like, but it's what you get, right? We still see the general trend of what we were supposed to get in that experiment. All right, so you're going to need to do that with your data so that you get to that point. I'll give you a few more minutes to work with the data, and then I'll talk about the analysis, because that's going to be kind of a big deal for this experiment. So I'll give you about another 10 minutes, and then I'll start talking about the data, or the analysis, sorry. So for much of the analysis, really all you're doing is filling in the chart. Okay, so if you look at like analysis question number 1, it says apply a linear fit to the motion sensor graph, so you do that. Okay, calculate the applied force value. Well, we already did that. That was the hanging mass multiplied by 9.81. Okay, so I filled that part in right here. Okay, so for trial 1, I went 0.05 kilograms, okay, and I multiplied that by 9.81, so I got my applied force. Okay, then it also wanted the acceleration, which was the slope of my graph for trial 1, so I just read it off the Google sheet. It was 1.22 meters per second squared. Just plugged it in there. Okay, and then for net force, okay, net force is the mass of the system, which for all of us is either 0.72 kilograms or 0.724 kilograms, depending on what color of cart you had, okay, multiplied by the acceleration. So I used the blue information, so I just went 0.72 times 1.22, and I got the net force here. Now, that's kind of the first few bits of the analysis. Okay, now, once we get done to number 3, number 4, 5, and 6 are the ones where you've got to write some stuff. It's not so much about calculating as much as it is about telling me what your data says, like actually doing analysis and interpretation. Okay? Up until now, your labs have been kind of cookbook. Do this calculation and tell me the number. Now it's going to be about what does your data say is happening? Okay, analyze your data. So for number 4, what's the relationship between net force and the acceleration of the cart? Well, all I have to do for that is look at my data and go, okay, so as net force went up, acceleration went up. And okay, that's good. That's kind of what I expected it to do. Okay, so I can say that. Okay, you've got to look at your data and say whatever your data says. Okay, but give me a bit of an explanation there. Question number 5 and question number 6 go together. And this is the part where you really got to look at your data and think about it. Okay? Question number 5 says, draw a free body diagram to describe the forces involved on the cart and the hanging mass. Okay? So here's my cart. It was 0.670 kilograms. Okay? And then I had a force going that way from what? Where did that force come from, guys? From gravity. That was my applied force. Okay? So I would have that. But here's the thing, guys. In our lab, we assumed that was the only force. Would you agree? Right? Did we take anything else into account there? We didn't. So theoretically then, my applied force and my net force should be what? They should be the same. Mine aren't. Yours won't be either. Now you got to look at that and tell me why. So when you draw your free body diagram, you got to think about, okay, my forces aren't equal. What was going on? Was there something working against the cart? Was there something working for the cart? okay? And your data might be different. Okay, you have to look at what your group's data says. This can actually go one of two ways. Sometimes people even have one trial where it went one way and another trial where it went the other. Okay, I had in this trial something was helping, but in this trial something was hindering, and you got to look at it from trial to trial. Okay, so when I'm looking at this, I see that my net force is larger than my applied force. I got to think about what that means in terms of the forces that were acting on the cart. Okay, everyone kind of follow me there? Okay, that's where you draw those forces into your free body diagram, and then in number 6, you've got to explain that. Come on. Okay, so in question number 6 it says, the net force and applied force are not equal in value. Explain why this is the case using your knowledge of Newton's second law. Okay, that is what I'm going to be really looking at when I mark your labs. Okay, I'm going to look at your data, I'll know what it says, and then I've got to look at your explanation and go, did they recognize what their data says? Okay, did they do a good job of explaining what happened in the lab for their group? Everyone follow what I'm talking about there? So there should be a bit of typing here. Okay, I'm looking for some fairly detailed explanations about what was going on based on your numbers in this lab for 5. Well, 5 is a picture, but 6 is the explanation of the picture. Okay? All right, conclusion, same as always. Copy paste your hypothesis. Can you accept it or reject it? Okay, did what you said in the hypothesis come to fruition in the lab? Okay, and then sources of error. I've already got a few people who figured out some. Okay, especially if you had a wooden ramp. Okay, there's a little thing that happens with the wooden ramp that doesn't happen with the metal ones, okay, and anything else you can think of that could be a source of error. Maybe things we didn't account for, okay. When we put it on the desk, did we check certain properties of it before we started doing the experiment? Things like that, okay. 2 sources of error and ways to fix them. Okay. All right. Questions from you guys? Okay. You can work for about another 6 minutes or so, and then we'll get the Chromebooks put away, okay? But you still got some time to work there.